covariant Gross-Pitaevskii-like equation for relativistic fermions.
You know what's wild? The way physicists have rewritten one of the most famous equations in quantum mechanics to make it fit a whole new class of particles. And they didn't just tweak it, they fundamentally changed how mass shows up in the math.
Wait, really? I thought the Dirac equation was already pretty solid for describing electrons and other fermions.
Exactly. But here's the twist. Instead of using a fixed number for mass, they made the effective mass depend on the particle's own field value, which sounds abstract until you realize it lets them keep the equation Lorentz invariant, meaning it works correctly in all reference frames.
So they basically gave mass a personality.
In a way, yes. They replaced that constant mass term with something that involves products of the wave function at different points. And this isn't just some math trick. It directly affects how particles behave when they interact strongly.
Interesting, but why would you want to do that?
Because in real systems like ultra-cold atomic gases or certain high-energy scenarios, mass isn't a simple number. It's tied up with the way particles couple and scatter, so this new form captures those effects more naturally.
Okay, I see how that could matter for simulations. But what about the actual equation? Does it still look like the usual Dirac thing?
It starts out similar, but then diverges because of that mass modification. They introduce a term involving scalar products and gamma matrices to ensure everything stays consistent under Lorentz transformations.
So you're basically extending Einstein's ideas into quantum particle dynamics in a clever way.
Precisely. And this approach opens the door for new kinds of predictions, especially when dealing with relativistic fermions that interact strongly, something standard Dirac theory struggles to handle without approximations.
That sounds powerful. So what comes next in the paper? All right, Jamie, we've been talking about the usual Dirac equation and how it describes particles with mass. But now they're saying there's a modification when coupling constants are small. What does that even mean?
Great question. Think of the standard Dirac equation as the baseline recipe for describing fermions, like electrons or quarks. It includes this mass term, which is a fundamental property that doesn't change under Lorentz transformations. It's a true scalar.
Okay, so mass stays mass. But what happens when we tweak it?
They adjust the mass term by introducing dependencies on other fields, specifically products of the fermion field and its conjugate. This new effective mass isn't just a constant anymore, it varies based on how these fields interact.
I see. So instead of one fixed number, you have something that changes depending on the situation?
The function f represents phenomenological interactions between fermions, basically how they influence each other in complex ways. It's like adding spices to a dish. Now the flavor mass can change based on what else is mixed in.
Interesting. And then there's this nonlinear Dirac equation that pops up later?
Right. When you include these interactions properly, the Lagrangian leads to a nonlinear version of the Dirac equation. It's similar to how gravity affects spacetime here. The fermion field itself modifies its own dynamics.
Nonlinearity is wild. So what's the big deal about this form?
Well, it resembles the Gross-Pitaevskii equation used for Bose-Einstein condensates, but here it applies to fermions under weak interactions. It lets us model scenarios where particles influence each other strongly in a quantum field.
And those Fears identities they mention?
Those are mathematical tools ensuring consistency when swapping particle and antiparticle states, kind of like double-checking your work in algebra to avoid mistakes. They enforce constraints between currents and generators, keeping the equations physically meaningful.
So it's all about capturing how fermions interact without making things too complicated.
It balances realism with manageability, acknowledging interactions exist, but simplifying them enough to extract useful predictions for systems where weak coupling applies.
This is actually pretty cool. Any hint of real-world applications?
By studying these nonlinear equations, researchers can simulate condensed matter setups or particle physics experiments involving weakly coupled fermion gases, opening doors to new quantum technologies.
Jamie, last time we were talking about how researchers tackle tricky physics problems with math. Now they're getting into something called the nonlinear Dirac equation under weak interaction. What's that all about? Dropping them completely sounds like cheating a bit. Is it valid?
Not exactly. It's more about focusing on the dominant effects first. They're essentially saying, let's ignore the weak stuff for now and see what happens, then add corrections later.
So they're doing an approximation, like ignoring background noise to hear the main melody?
And it works because in many cases those small constants mean their effects are negligible at first glance. But you still need math to clean up the details.
So what happens next after they set this up? They mention moving into momentum space and using Green's functions?
Ah yes, once in momentum space, it's easier to handle interactions mathematically. The solution involves something called a Dirac bispinor in the whale representation, basically breaking down particle behavior into spin components.
Spin? So particles have this intrinsic rotation thing going on?
And they're looking at occupancy numbers for particles and antiparticles, which tells you how many are in each state. Then corrections come from terms linear in those tiny coupling constants.
That makes sense, like fine-tuning a model to get the right answer without overcomplicating things up front.
And they're careful about what's physically meaningful, ensuring only relevant effects survive. The whole thing ties back to real-world quantum systems where weak forces dominate.
So if I understand correctly, they're building a simplified model that still captures essential physics without getting lost in the weeds?
It's about balancing simplicity and accuracy, a common dance in theoretical physics. And honestly, it's pretty clever how they isolate what really matters.
That's actually kind of inspiring how you can strip things down yet still get something powerful out of them.
But remember, this is just one piece. They'll need to check if these approximations hold in more complex scenarios later on.
Jamie, we're getting into something pretty heavy here. Quark confinement through the lens of a nonlinear Dirac equation. So what's the big picture?
Alex, they're taking this idea from quantum chromodynamics, the standard model that describes how quarks behave, and trying to apply it in a new way using this Dirac framework. The goal is to see if they can mathematically capture why quarks are always confined within particles like protons and neutrons.
So what's the starting point? It sounds like they're narrowing their focus to just one version of quantum field theory, the QED case, but then extend it somehow. How does that work?
They begin with a specific setup where they simplify things by assuming certain properties about how quarks interact, especially focusing on the current and the mathematical operations involved in their equations.
So they make some approximations to make it tractable, like ignoring position dependence for certain terms? That seems like a common strategy in theoretical physics.
They simplify by separating variables into momentum space, which lets them handle the problem more easily while still capturing essential features of confinement through the structure of their equations.
And then they switch to non-relativistic limits? Why would they do that if we're dealing with quarks in the first place?
They do this because many properties relevant to low-energy phenomena, like superconductivity analogies, they can be studied more straightforwardly without relativistic complications, even though quarks themselves are highly relativistic.
So they're building a bridge between high-energy particle physics and condensed matter concepts like superconductivity? That's clever.
They're using this model to see if similar mathematical structures can describe phenomena across different domains, linking up quark behavior with familiar patterns seen in materials such as superconductors.
And what happens when they actually look at the equations? What do they end up showing about the energy gaps or dispersion relations?
They derive a dispersion law that matches expectations from existing models like BCS theory, and importantly, the gap parameter relates directly to parameters in their extension of the Dirac equation. This consistency is what makes the approach promising.
So if I understand correctly, this isn't solving quark confinement outright, but showing how certain mathematical forms can reproduce known behaviors under specific conditions?
Exactly. This is a step toward understanding, not a final solution. They're testing whether extending the Dirac equation in these ways captures key features without getting bogged down by unnecessary complexity.
That sounds like solid science with real potential for broader insight into both particle physics and applied models. I appreciate you walking me through it, Jamie. Alright, so we've got this paper talking about quarks and how they stick together really tightly, almost like they're glued. The big question is why we don't see free quarks in nature. So the paper uses this equation and applies something called the Kogut-Susskind approach to study confinement probability. Wait, what's the Kogut-Susskind idea?
It's a clever trick from theoretical physics that helps analyze how particles behave in certain quantum field theories. They rewrite the problem using Wilson loops. Imagine tracing paths around quarks on a Feynman diagram to see if they can escape or not.
Oh, like drawing loops and checking if they trap the quarks?
The paper shows that for large enough time, the probability of finding free quarks drops to 0. They're forever confined.
That's wild. And it gets even more interesting because this approach also ties into real-world models like quark-gluon plasmas and superconductivity. So they're not just solving math puzzles. They're trying to explain what happens inside stars or in particle accelerators.
The nonlinear Dirac equation here is a step toward making sense of those extreme environments where normal rules break down.
And by using functional determinants and momentum operators, they can actually calculate probabilities for confinement scenarios. That's some serious number crunching. But why does this matter beyond physics class?
Because understanding confinement helps us build better models for everything from nuclear reactors to the early universe. It's all about how matter holds together at its most fundamental level.
I never realized a math equation could tell us so much about the universe's building blocks.
That's the beauty of theoretical physics, taking abstract ideas and turning them into tools that reveal hidden truths.
But let me ask, if this is so advanced, how do we even test these predictions?
They often compare theory with experiments like those at the Large Hadron Collider, or study heavy ion collisions where quark-gluon plasma forms briefly.
So they're watching tiny fireballs to see if quarks behave as predicted?
And when the data matches up, it gives us confidence that we're on the right track.
Makes me appreciate how science connects math, theory, and real experiments.
And this paper adds a new twist by showing how nonlinear equations can capture confinement without needing to solve every detail directly.
That's clever, using approximations smartly instead of brute force.
Exactly the kind of ingenuity that pushes science forward.
I think we've only scratched the surface here. This topic is deep and full of surprises.
It really is. And if you're curious about what happens when they push this model further, like going beyond just quarks, they might run into some surprising limits or new phenomena that challenge our current understanding.
Like what?
Possibly uncovering situations where the nonlinear effects become so strong they rewrite the rules entirely, maybe even hinting at unknown physics waiting to be discovered.
That sounds like the kind of mystery that keeps scientists up at night.
And that's why this work matters. It opens doors to new questions and possibilities we haven't even imagined yet.
So we've been talking about this paper that proposes a new way to model interactions between fermions using something called a nonlinear GP-like Dirac equation. Jamie, can you break down what makes this approach special and how it fits into the bigger picture of physics research? So it feels more like a clever refinement than a revolution?
Pretty much. The real value is in showing how nonlinear terms can better capture phonon-mediated interactions without sacrificing covariance, a fancy way of saying the math works consistently across different reference frames. It's about bridging gaps between theory and observable effects.
And what does this mean for practical applications down the line?
Honestly, it depends on how well their predictions match experimental data. If they can accurately model phenomena like confinement in quantum chromodynamics or exotic states of matter, that's a win. But we're still at the stage where theory needs more real-world validation.
Sounds like an exciting step forward with lots of potential, but also some caution needed when interpreting results.
Exactly. No silver bullets here. The authors emphasize that their model is one tool among many, useful for specific scenarios, but not a universal solution. It's about expanding options rather than declaring victory.
Thanks for walking us through this, Jamie. I always appreciate how you keep things clear and grounded in the real science behind these ideas.
Anytime, Alex. And to our listeners, keep that curiosity alive. Science isn't just about answers, it's about asking better questions every day.
That's all we have for today. Thanks for listening, everyone.
See you next time.